Hello everyone and welcome again. My name is Allison Sterling and I'm a Marketing Manager with Emerson Flow Solutions, and I'm pleased to welcome you to our Emerson Flow Expert webinar series and our webinar, Advances in Multiphase Metering for Onshore Measurement in Oil and Gas. Before we begin today, I just want to take a brief moment to acquaint you with your webinar environment. On your screen, you should see on your left-hand side there a presentation window. A Q&A chat window will be in the upper right-hand corner. There'll be media player controls and a resource box with some related content there that you can view and download during the event. You can also resize, move, minimize, or any of these windows to fit your viewing preferences. And at the bottom of your screen, you're going to see a row of icons there that give you some added capabilities where you could choose to share this webinar via social channels or even request a visit from one of our flow experts. Throughout the webinar, we encourage you to interact with our speaker by typing in questions using the Q&A chat panel, and we will be answering all questions at the end of the webinar, so we'll be holding them till then. We are also recording today's webinar, and we will make a link to this recording available to you 24 hours post-event via email, where we will also share with you a link to the resources you see on that sidebar. On today's webinar, we are lucky enough to have you joining us. And for some reason, I don't know why, there we go. Sorry, I couldn't move my slides forward. We are lucky enough to have joining us Laura Schaefer, Lars Anders Ruden, and Martijn Tall. Laura Schaefer is the Vice President of Oil and Gas for Emerson Flow. And with more than 15 years of experience in the oil and gas industry, Laura joined Emerson in 2012 with a focus on extending flow measurement applications in oil and gas. Her experience spans from drilling and completions to production. Lars Anders Ruden is the Strategic Marketing Manager for Roxar Flow Metering Products with Emerson. With more than 18 years of experience in the oil and gas industry, Lars joined Roxar in 2004 with a focus on multi-phase flow metering. His experience spans from drilling and completion, upstream flow metering, to strategic business development. Martijn Tall is the Product Manager for Roxar Topside Flow Metering Products with Emerson. With more than 10 years of experience in the oil and gas industry, Martijn joined Roxar in 2006 with a focus on multi-phase flow metering. His experience spans from upstream flow metering to product management. Welcome, everyone. Laura, the floor is yours.
Thank you, Allison. And thanks to all you on the phone who are taking time to learn how and why multi-phase measurement is gaining traction in North America for allocation measurement. So when oil was over $100 per barrel, remember the good days? Many of us didn't have time to evaluate and look for new methods to reduce our spending. We were all busy drilling the next well. But when oil dropped to $30 per barrel, we've all been asked to identify ways to reduce spending. You can see it on every corporate presentation to investors, right alongside, quote, improve field performance through technology and innovation and identify efficiency improvements, et cetera, et cetera. In this presentation, we'll step through the need for multi-phase measurement and the status quo for facilities and how we can change those facilities with the multi-phase meter. We'll introduce the Emerson portfolio of multi-phase measurement solutions, including a micromotion Coriolis meter for low gas wells and Roxar's modular multi-phase meter, the 2600 MVG. We'll present the value that customers have seen to date and then wrap up with that Q&A session. So don't forget you've got that Q&A button at the bottom. Don't hesitate to drop in questions as you have them. So let's start by looking at the aspects for consideration when selecting a pad architecture and measurement technology. Up in the top left corner, we have asset optimization. This relates to producing as much as possible at as low a cost as possible. Two focus areas are reservoir and well optimization, considering process or environmental constraints. Consider the greater control that operators have when they know more about what they are producing and at what volumes, and how adjustments can be made with this knowledge to optimize production. The rise of automated workflows, some available from Emerson, allow some of this optimization, especially around artificial lift, to be handled automatically, driving dollars to your bottom line without the need for personalized attention. All this optimization must be balanced against constraints such as ability to handle water, need for gas flaring, downstream capacity, etc. So continuous real-time information becomes absolutely critical to realizing these optimization efforts. In number 2, bottom left, process integrity and safety includes monitoring and controlling the risk for deposits in your well and facility, such as scale, wax, hydrates, as well as corrosion and erosion. Although insight into scale and wax deposition is not the aim of a multiphase meter, detecting small changes in water production is, which can provide valuable information to you to take actions to prevent and reduce the potential for hydrate and scale formation. Moving on to number 3, transactions and allocations. Many assets have joint ownership or points where flow from one asset join a pipeline that's transporting flow from another asset with different ownership. Therefore, quality measurement is absolutely required there to establish the volumes from each asset in order to correctly allocate the financial gain. Finally, in number 4, regulations and governmental requirements must be adhered to and often reference industry bodies such as AGA, API, ISO. Those regulations and accuracy requirements vary widely between countries, between states, and owners who may have their own requirements in addition to the governmental regulations. All of the 4 aspects here involve measurement of the well's production somehow, either as a multi-phase meter or single-phase flows. Historically, the majority of these measurement needs have been handled with separation followed by measurement. So of the 4 aspects, we'll just do a little question here to get folks engaged. What is the primary driver for your selection of well pad architecture and flow measurement technology? The breakdown here will provide me a bit of insight on what's important to you. As I continue through the webinar, I can focus on what's important to the folks attending. So please select the answer that indicates your view of that primary driver, and then hit submit on the bottom right. So is it allocation, fiscal custody transfer, reservoir and well monitoring, production optimization, or flow assurance? We'll give a moment for folks to answer. Now let's take a look at the answers. Whoop, there we go. All right, so the majority of folks on this webinar are stating allocation is the most important driver for the measurement technology. So that's 29.3%. This is interesting because we just did this webinar with Asia Pacific last night, and the number 1 for them was reservoir and well monitoring. You can tell here in the U.S., we're definitely driven by the need to pay those royalty owners. So let's take a look at those traditional measurement techniques and pad layouts, and then move forward and see how those can be improved with multi-phase measurement. So traditional methods of measuring oil, gas, and water, they do not tolerate multiple phases well. Flow meters such as turbine and positive displacement meters can be damaged if multiple phases occur. For example, overspin when bubbles pass through a liquid meter, not to mention the damage that sand could cause. Other flow meters, such as differential pressure meters, can often tolerate the presence of multiple phases, but cannot measure the individual phases when commingled. So, for example, on that chart, that just graphic there that shows flow versus time, if you see an increase or decrease in flow, it's very difficult to tell, is that a real increase or decrease, or is that multiple phases in my flow? While substantial effort has been invested in developing correlations and models to enable indirect estimation of the quantities of multiple phases in these single-phase technologies, the assumptions tend to break down over time as the flow and production characteristics of the well change. Take a Venturi meter on wet gas, for example. I need to input a number of correction factors, including Lockhart-Martinelli number and the density ratio. As production changes, it's challenging to differentiate between those true increases or decreases in flow rate versus gas to liquid ratio. Throughout the well's life, the correction factors will change, necessitating sampling or regular well testing. And those systems, they add extra cost and carry their own sets of uncertainty. So with the large amount of instrumentation on a separator, simple maintenance issues can lead to significant uncertainty as well. Whether it's a leaky valve, faulty level control, or an out-of-commission heating element, all of this can lead to higher uncertainty than we should have, considering the investment we've made in that separator. So in spite of that uncertainty, the typical well pad architecture consists of a combination of separator and traditional flow measurement technology. The figure on the left illustrates a conventional test and production separation arrangement, and this arrangement requires a significant number of valves, piping, duplicate instrumentation on each separator, etc. Additionally, to change the well under test, actuators with attendant automation are required to avoid the need for continuous manual intervention. Even with automation, the residence time of the separator, that test separator, it necessitates tests of many hours or even days to get a good number. And that significantly impacts the resolution of data achievable for that single well. Some producers I've spoken with get a data point or two from a well once every 2 months or so. That's not often enough for our reservoir and production engineers. If a data point looks funny or doesn't quite jive with the previous data, it may be months before that point can be checked again, and that might be potential lost production that whole time you're waiting for that new point. A few other challenges with this arrangement. One is that the setup is designed for the average or max production from each well. So if all wells on the pad are not designed or expected to be in the same range, the separator and flow technology could struggle to maintain accuracy over the life of the field, giving fair results for some wells, but less accurate results for the lower producers. Additionally, if completion techniques improve and a new drill on the pad has substantially higher production than the original separator design has capacity, then that initial production measurement will suffer as well. With the rise of unconventional plays in the last several years, the need for continuous insight into a well's production, those dramatic decline curves, long horizontals, etc., the need to estimate an accurate EUR from those initial first couple months of production, all of that has driven a switch from the test production arrangement on the left-hand side to a one-for-one, in which each well has its own dedicated separator and measurement technology. This results in some pads having 5, 10, even up to 20 or more separators on a single pad. That's tremendous capital expense. In the last year and a half in particular, onshore operators are looking for ways to reduce the capital expense on the pad. The figure on the right shows a well pad design that requires significantly less piping, it's a smaller footprint, and it reduces intervention and maintenance requirements. We can realize this layout using direct wellhead measurement with multi-phase meters. So each of those little circles with the blue circle in the center, those are each representing multi-phase meters. So with the multi-phase meter, each well can be tested individually and continuously without having to redirect individual well flow to a test line. This eliminates the need for additional automation or manual intervention to test the well. A third variant on the well pad arrangement would keep the manifold from the figure on the left and simply replace the test separator with a single multi-phase flow meter. This is particularly beneficial for operators seeking to reduce their footprint, particularly in cases onshore where land is at a premium. The multi-phase meter in the arrangement provides the benefit of reduced residence time for faster cycling of tested wells, requiring minutes instead of hours. You don't have that huge separator tank that you have to cycle well fluid through to get an accurate picture. This allows you to get more test data more frequently with less uncertainty, and improving the usability and resolution of the data for the reservoir and production engineers. So with this concept, many producers are evolving their philosophy over the last couple of years. So if you had a multi-phase meter that you could trust, how would you like to collect well flow measurement in the future? Select the answer here that is closest to your future facility plans or desires, then go ahead and submit your answer clicking on the bottom right. We'll review the results in a moment. So we've got a lot of different options here that are from many, many different operators that we've interacted with over the years. Different philosophies. We've got multi-phase meters at each well, which will be the focus of this presentation. But then we've seen many, many variants with 3-phase, 2-phase, even manual sampling, tank measurements, etc. So we'll give you a second Let's go ahead and look at those results. So, well, that's excellent. I suppose that's why everyone's on the call. So 77% of folks said that they were interested in the multi-phase meters at each well. Interesting, we've got 13.6% who said that they were interested in virtual metering systems. We'll definitely be able to maybe speak to that at the end if we have time, so please submit your questions. All right. So why can't we get to the multi-phase on every well? What's stopping us? Well, historically, concerns around the expense and the reliability and the flexibility of the technology have hindered adoption. Taking a look at each of these challenges, performance, flexibility, and cost efficiency, we can break down each of these challenges that we have to address. So one being cost-efficient meters. We need meters that cover different application needs in a more cost-effective manner, particularly if you have a test separator arrangement where the meter would need to function for many wells with very different production characteristics, or wells that have dramatic reductions in flow or change in gas-oil ratio over the life of the well, very similar to shale wells, right? The solution needs to handle all of these conditions and more. The second challenge, access to high-quality data to maximize field revenue. This is all around increasing production efficiencies and maximizing that field revenue. The data is the whole reason that we're measuring in the first place. And so I need to be able to count on that data, not only to be able to optimize my field, but also to pay my royalty owners and the government. And then third, a metering solution that evolves and provides flexibility over the time. That meter needs to last the lifetime of the well. I can't afford, particularly on these unconventional wells, to have to change it out 5 years down the road as the production has declined significantly. That pad needs to run itself 5 years from now. So many meter types have significant turndown limitations and require changing of that primary element and piping to cope with the changing well conditions. So we're looking for a meter that has large turndown and robustness to change. All right, so we've covered the challenges. Let's take a look at the multi-phase metering in depth. And let's explore why we haven't had a good solution, particularly for onshore up to now. So multi-phase measurement provides the individual phase flow rates for oil, water, and gas mixtures. Some examples of multi-phase flow are shown here, with each phase shown in a different color. The complexity of possible flow regimes in multi-phase measurement necessitates multiple technologies to interpret these complex flows, particularly as they change over time. Just a few years ago, multi-phase meters were either far too expensive for onshore consideration, or the affordable models on the market were inconsistent in operation or had a very, very small window in which they did operate, requiring continuous recalibration throughout the year and leading to uncertainty as to whether the meter was giving you accurate data or not at all. But as oil and gas producers have had to adapt to the lower prices of today, likewise Emerson has had to adapt as well. So leveraging years of Rockstar experience in offshore and subsea markets, as well as Micromotion's more than 35 years experience with Coriolis technology, we're introducing a portfolio of options to meet the challenge of reliable data, flexibility, and efficiency. So here's the portfolio from left to right. On the left is the elite Coriolis meter with the 5700 transmitter and the advanced phase measurement software package from Micromotion. While the Coriolis is truly a single-phase technology, the use of density measurement along with advanced diagnostics allows for more accurate measurement of the liquid phase for gas void fractions less than 15%, or measurement of gas for gas void fractions greater than 95%. So that's a wet gas type measurement. The meter is best suited for wells with extremely low gas content or dry gas wells with limited liquid. So I'll show a table of specifications later, so don't worry about writing it down or keeping track of that, okay? We'll go through those specifications with uncertainties in detail later. The second to fifth meters shown are variations of the new Rockstar 2600 modular multi-phase meter. This flexible platform allows producers to purchase just the modules they need for the accuracy required and production characteristics expected. I'll step through the two technologies in the next few slides, then illustrate how to select the right technology based on your conditions for your well. So first, Coriolis flow measurement. Coriolis flow meters independently measure mass flow rate and density. The density, along with the diagnostic called drive gain, can be used to positively identify the presence of multiphase flow. Drive gain is low whenever the flow through the meter is all liquid or all gas. When a bubble is present in the liquid or a droplet is present in the gas, the drive gain responds immediately, increasing rapidly. So in the chart on the right, we see a density change in the liquid flow. That's the curve in the gray. But the drive gain in orange remains low. Since the drive gain remains low, we know with confidence that there's still only liquid present. So with confidence, we know that a composition change has occurred within the liquid. For example, an increase or decrease in water cut. Here we're looking at an increase in water cut. In the case that a density decrease is accompanied by a spike in drive gain, we know with confidence that this isn't a decrease in water cut, but that it is a definite indicator of bubbles within the liquid phase. Conversely, the same is true for gas flows. A density increase coupled with a drive gain increase indicates the presence of liquid within a gas flow. So utilizing the power of both density and drive gain, the Coriolis software enhancement advanced phase measurement was introduced earlier this year. I'll review advanced phase measurement very briefly in the next slides, but for those who want to learn more, go ahead and reference the link to my webinar on advanced phase measurement in the resources tab in this webinar interface and bookmark it for later. So that resource tab is at the bottom there, or you might have it open already. So advanced phase measurement is going to provide plus minus 3% liquid accuracy and up to 15% gas volume fraction, as well as improved wet gas performance once best practices are followed. So it's very important to follow the best practices to get those sorts of accuracies. You can't just install and assume you're going to get 3%. Advanced phase measurement consists of 3 feature keys that can be independently activated. The first is PO, and that's a net oil application that can either calculate water cut based on user input densities, or it can accept a water cut value from an external device. The PL key provides the ability to remediate liquid process values in the presence of gas. So PO and PL can be combined to get net oil calculations in the presence of limited amounts of gas. Finally, the PG key provides the same approach except to gas applications with mist or liquid, so the wet gas. APM has primarily, since we've introduced it, it's primarily found application on oil outlets of poorly performing separators, whether they're undersized or on plunger lift, etc. APM can dramatically assist in achieving more confidence in that allocation measurement off a poorly performing separator. We also have application for APM for heavy oil or old brownfield wells with very low gas content. The Coriolis meter with advanced phase measurement can present a great low-cost option for that. For slightly gassier wells, some customers are using just a simple gas knockout followed by a Coriolis liquid stream measurement, and that can be an affordable alternative to, say, a full multi-phase meter. Advanced phase measurement has also been used to tackle gas measurement with entrained mist or liquid on separator gas allocation and directly off the wellhead. So we've been measuring naturally lifted gas wells and plunger lifted wells with advanced phase measurement. So the Coriolis can be an excellent solution. However, most wells, let's face it, especially in the U.S., most wells are not less than 15% gas void fraction. Or if they are, they won't remain below 15% throughout the life of the well. This is where the true multi-phase meter, Roxar's 2600, is extremely well suited. So Roxar has developed this flexible, cost-effective meter for measurement needs at the wellhead in place of a test separator or in flowback monitoring. The 2600 MVG shown here can help increase efficiencies and enhance production, making marginal fields more viable. We can size this to meet expected initial production rates through to mid and late life wells with 1 meter, eliminating the need to increase the CAPEX spend on larger test separators that will only be used at capacity for a very short period of time. Rockstar's 2600 also reduces the need for additional equipment and measurement devices, resulting in fewer troubleshooting site visits, etc. So it really gives you a lot of flexibility on the measurement. So let's take a closer look at the meter itself. The main components of the 2600 MVG are the 3 primary measurement techniques. So on the right, from top to bottom, are the Venturi, the impedance measurement, and the gamma system. Note that the Venturi has a field replaceable sleeve, as mentioned right there, and that allows operators to reduce or increase the beta ratio of the flow measurement throughout the life of the meter or throughout the life of the well or pad. That gives you a lot of flexibility and much greater turndown availability in a single instrument. On the left, we have associated components. So we've got the multivariable transmitter and compact manifold for the DP measurement across the Venturi, and then the EXI-rated field electronics. This is the fully loaded multiphase meter, the MVG. The innovation here is that many applications don't require all of these measurements. So what if you could purchase only what you need? On the left side of this slide, we see the 2600M. Note I said M and not MVG. So there are 4 add-on modules available for the M that can be combined in different ways to meet the needs of different applications. Note that the Venturi section and the gamma section are both independent modules that can be mixed and matched onto the base 2600M to achieve the measurement you require, giving flexibility in pricing. On the far right are 2 additional modules, a software add-on for wet gas mode and a salinity measurement model, that RMSS, that can be added on as required for a well. So let's meet the family. Starting in the upper left-hand corner, we have the 2600M, the base module that is a well monitoring tool for trending water cut, gas breakthrough, and flow rates. That's what it's ideal for. If you add a Venturi to the 2600M, on the bottom left, you get the 2600MV. So notice we've added the V for Venturi. So this is ideal for high accuracy flow rates for oil, water, and gas over a much broader range of applications. If you add a gamma system to the 2600M, and that's on the top right, you get the 2600MG. Notice we added a G for gamma. Fairly logical. The addition of that gamma system improves accuracy and robustness of the meter. So if you like the 2600M but you need a little more accuracy, you can add the gamma. Finally, on the bottom right, we have the complete MVG, which has the impedance, Venturi, and gamma modules all stacked. This meter can be used for both a single well or multi-well application and gives the best accuracy with the widest range of conditions that it can cover. So let's look at these meter versions one more time with the combination of different add-on modules to just demonstrate how these can be stacked. So if we start with the 2600M, we can then add on the Venturi module to have the 2600MV. Further to that, we can then add wet gas software module to apply the 2600MV to much, much higher GVF, so 98% to 100%. Although this is not the most common add-on for the 2600MV, the salinity module can also be added on. So note that you can get up to 100% GVF you can get extremely good high GVF measurement without a gamma unit there with that 2600 MV wet gas mode. So just keep that in mind. So on each of these, no gamma. So for each, you can add the gamma for improved accuracy. This means that the 2600M, you can add the gamma to get the MG. Same thing, you can add the gamma to each of these to improve the performance of each. So that's how this modular platform is stackable and can be retrofitted in the field with any of these modules. So now that you get the stackability of it, I'd like to pause and ask, what are the primary parameters you wish to monitor from your well? You can select multiple answers here, so pick as many as are relevant for you, and then hit submit, and we'll just review the answers. So pressure and temperature, water cut, gas-oil ratio, total mass flow rate, individual flow rates, or oil rate only. All right, not too surprising here. Folks are most interested in the individual flow rates of oil, gas, and water. The good news for all of these is that all of them and more are actually available out of each of these multi-phase meters. So let's learn how each version delivers its measurement. So let's start with the simplest module. That's the 2600M. So it only has the impedance measurement contained within that module. So how does it get 3 flow rates? Well, the non-gamma model performs rapid time series analysis to find liquid dominant periods in order to provide the gas to liquid ratio. If the water liquid ratio or the gas oil ratio is known, that can be used as a fixed input, but it's not required, okay? The velocity is then obtained from the cross correlation. So this technique still provides flow measurement for all 3 phases. I'll talk about cross correlation in a few slides. For the 2600 mg, you've added the gamma system, and so that enhances the measurement because the gamma is then used to determine mixture density of the flow, giving you more accurate cut between your oil, water, and gas. The velocity here is still obtained from cross correlation in the impedance module. So you're still getting all measurement of oil, water, and gas from this module. You're just enhancing it with that density measurement. For the 2600 MV, velocities are now calculated both from cross correlation in the impedance module and from the added Venturi measurement. So with that MV, of course, V for Venturi, you've got that Venturi on top, contributing to the accuracy of the velocity. Since this unit does not sport that gamma source, the non-gamma model is still performing that rapid time series analysis to split between liquid and gas. If a water-liquid ratio, again, is known or the gas-oil ratio is known, that can be used as a fixed input, but again, it is not required. So finally, the 2600 MVG uses the combination of gamma electrical impedance for determining phase fractions. It uses the cross correlation and the Venturi for velocity measurements. And with the gamma system used for measuring the mixture density for the flow, it gives the highest accuracy over the broadest range of conditions. So hopefully that gives you insight on how each of these modules is providing you a measurement. I wanted to revisit that cross correlation. Mentioned that earlier as the technique uses to determine the velocity in the 2600M and the 2600MG. So with cross correlation, we've only got the impedance measurement, but we've got 2 sets of sensors for the impedance. As packets of liquid and gas pass first one set of impedance sensors and then the second set of sensors, the time difference between the signals at the 2 sets of sensors is then used to calculate velocity. This technique has historically been used by Roxar to measure gas velocity and therefore determine phase slip, independent of the liquid velocity. So this modeling then gives you 2 velocities, one for the gas and one for the liquid. So now that we understand the operation, let's look at uncertainty, because I'm sure everyone's wondering, how accurate is this measurement? So this table shows the recommended operating envelopes and typical uncertainties for each of the meter modular stacks. So this information is also available in the product data sheet, and that's available in your resource tab in this webinar interface, so feel free to download that at any time. The operating range of a meter is defined by the gas volume fraction and by the water liquid ratio. Notice that all meter versions are suitable for the measurement for the full 0 to 100% water liquid ratio. So regardless of your water cut, there's no restrictions here. Your restriction is going to be on the gas volume fraction. So the 2600 M, mg, and mv all have an operating range of 0 to 85%. The 2600 MV will provide flow rates throughout that range. However, the 2600 M and MG versions will provide flow rates only from 15 to 85% GVF. At less than 15% gas void fraction, they'll only give that water liquid ratio. Okay? If wet gas mode is added to the 2600 MV, it could now be suitable from 95 to 100% gas void fraction. And the 2600 MVG, the complete stacked version, that one has an operating range of 0 to 98%, and that can be extended then to 100% with the inclusion of wet gas mode. So, where can I put a 2600 multi-phase meter? Well, basically anywhere you want. From onshore to subsea, skid-mounted or inline, we've successfully installed and operated in all of these environments. And speaking of success, we have nearly 500 2600 meters delivered globally to date. So quite the installed base to draw experience from, and definitely you wouldn't be the first person to purchase one of these around the world. So I've shown both Coriolis and multi-phase meters here. How do I choose the right technology for my well? So we can use this chart here as part of the reference. So from left to right on the chart's x-axis, we see the GVF range for operation. The micromotion Coriolis is on the far left, operating in less than 15% gas void fraction with that accuracy of approximately plus minus 3%. Note that the Coriolis will provide liquid rate and a gas void fraction, but will not provide a gas total. For flows with frequent gas bubbles, it is recommended to pair that Coriolis with a water cut meter to ensure that the net oil and net water are correctly accounted for. Likewise, the Coriolis is capable of measuring the gas at gas void fractions greater than 95% and can estimate the total liquid produced, though it will not discriminate between oil and water in the wet gas range. That's not shown on this graphic, but that is available. We have no accuracy statement for that particular use, though, so it's definitely more for insight into a well than necessarily for true allocation. For reporting of all three phases, gas, oil, and liquid, the 2600 platform provides rates for all three. On the left side, you can see approximate price comparison for the technology for reference. So you can see how each of these sit in relation to what you might be more familiar with as far as the cost of that Coriolis. So of course, the Coriolis is the least cost, but it is the most restrictive in its range of operating conditions. Actual pricing will depend on metallurgy selected, meter size, flanges, etc. So if you're interested in a quote for your application, please contact us. Don't assume that it's going to be out of your price range. Definitely contact us and let us know what your application is and how many you're looking for, because that makes a difference. The second extremely important consideration when selecting a meter is how your well and reservoir production may change over time. On the left, you see a diagram where pure oil is represented in the bottom left, pure water in the bottom right, and then pure gas at the top vertice of that triangle. A measurement point in the bottom left would be akin to a measurement off a LACT unit where oil should be merchantable, and the measurement should be made with a Coriolis or PD. I mean, it's a single phase, so use a single phase technology. In this case, let's look at well 1. Which the reservoir engineer predicts will have a 10% gas void fraction over the life of the well, and it will shift over time, becoming much higher in water cut, but will have minimal increase in gas liquid ratio. So you see that second number 1 over to the right. This well could be a great candidate for Coriolis with advanced phase measurement if the reservoir and production engineers are not interested in the gas rates. Recall the Coriolis solution gives real-time gas void fraction, but does not calculate a gas total or gas rate. If the engineers are interested in that gas flow as well, then the 2600 MV would be a good option here. In the event that well 1 is expected to get gassier over time, you see how 1 shifts up in the triangle, then a Coriolis should not be considered. Even though it might work on day 1 for that well, over time it would no longer work. And rather, it'd be ideal to select either a 2600 MV or MVG, depending on your accuracy requirements. So if we consider a second well, the well both starts and ends in the ideal range for a multi-phase meter. So here you could use the 2600M, MV, or MVG. All could work, just depending on your accuracy requirements. So returning to our 3 operator challenges, cost efficiency, high quality data, and flexibility over the life of the well, let's look at how the multi-phase portfolio of solutions presented answers each of these concerns. So we've shown a flexible multi-phase portfolio that allows significant reduction in capital expense on a pad, significant space and weight reduction, particular to offshore for that weight reduction. And then the meter is easy to install with low power consumption and can be quickly and efficiently set up. With any of the meters shown, whether Coriolis or multi-phase meter, you're going to receive reliable quality data with immediate alerts to changes in flow rate, composition, and gas void fraction. And finally, with the 2600M platform, you can retrofit your meter at any time, paying for only the features you need now. That field replaceable Venturi sleeve increases the meter turn down, and that's ideal when flow rates or field decline rates are uncertain. So let's pause for a final question before looking at the results achieved by some of the customers out there. What benefits might you achieve by switching to inline multi-phase metering? This is a multi-select, so please select all that you believe apply and go ahead and hit submit. So reduce CAPEX, OPEX, real-time measurement, optimization. Let's see. All right, so we've got reduced CAPEX costs for well pad design from 71% of the respondents. And definitely that is one of the first things that U.S. producers have seen as a result. With hundreds of multi-phase meters installed around the world, the introduction of this new platform with the affordable price point is what's going to make the difference here in North America. Working with customers, we have received feedback that in the Bakken, they achieve a savings of more than 50% on their facility CAPEX. For customers who have installed that multi-phase meter with continuous insight coupled with artificial lift optimization programs, they've realized 4 to 20% more production than natural decline of the well would project. So those customers, and they were offshore customers, they realized $5 to $20 million in additional revenue per year from those platforms. So that's using that continuous insight from the multi-phase meter with artificial lift optimization programs. Speaking of offshore, operators are also realizing over 100-fold savings in weight and significant savings in footprint, and certainly some of the onshore producers can tighten up their well pad designs with this sort of facility design. This snapshot is from a meter during a 24-hour well test being performed during flowback. This gives you a feel for the information immediately available from the multi-phase meter. You see the meter is measuring in actual conditions, and with the use of PVT data, it converts those real-time into standard conditions. The blue lines represent water, red is oil, and green is gas. We all know that these wells do not produce at a steady, consistent rate of oil, water, and gas. And here we can see the slugging and changes that are occurring as that well flows back. You can also see circled in the middle bottom right there, you can see a choke change, and you can see how that impacts the flow back as well. So even on challenging applications like flowback after fracking, this multi-phase meter can be used because there's no parts to be damaged by that sand. You can use this during that flowback and get your IP as accurately as possible. Operators that have had experience with this 2600 platform have also devised new facility and measurement architectures based on the strengths of this platform. in this installation that I'm showing here, this customer installed the 2600 Ms, the simplest of the modular multi-phase meters for measurement at each of the wellheads. So right there at the bottom by that label oil wells. The 2600 Ms are then all connected via manifold to a full 2600 MVG, and that would be in the top left there. That meter serves as the test meter and is used to regularly verify and calibrate those 2600 Ms, yielding top quality multi-phase measurement at all times for a lower overall total installed cost. So that was a rather ingenious way to use that new modular platform to get accurate measurement throughout that entire facility for low cost. So in summary, Emerson has developed a flexible, cost-effective portfolio of multi-phase solutions that enable operators to take significant steps closer towards cost-efficient, high-quality, continuous data from their wells. With that, I'd like to save the last few minutes for any questions you might have. So please click on that Q&A tab and submit any questions you might have for Lars, Martijn, and myself. Appreciate that. And I'll turn it back over to you, Allison.
Thanks so much, Laura, for such a great presentation on this great information. As Laura just mentioned, we're now going to open up for questions. So you can use the Q&A chat panel there to type in your questions. And it looks like we actually have quite a queue full of questions. So I think, Lars, I'll get you started on some.
Yeah, thank you. Laura, maybe this one is for you, actually. On slide 31, you're saying for high GVF application condensate wells, Coriolis with APM is better than 2600. Maybe you want to elaborate on that versus the wet gas mode?
On slide which?
31.
31. Probably not 31, perhaps 32. So for wet gas measurement, we have no accuracy statement for the Coriolis on extremely high GVFs. So I do want to clarify that the Coriolis is not better than the 2600 for wet gas measurement. The multi-phase measurement very much so will give you much greater accuracy there because the Coriolis is not guaranteed for any accuracy. However, it has been installed on a number of applications where the customers are looking for insight, trends, etc., on the amount of liquid coming in their gas wells, whether that's naturally lifted or plunger lifted. So it's a really great application if you're not being held to necessarily an allocation or transactional point there. So hopefully that's clarified that the Coriolis is not a competitor for that 2600, particularly whenever allocation is involved.
Thank you. Let's see, I'm trying to look through these questions. I mean, we have one here. Martijn, maybe you can answer this. Have you implemented the skid with the Rockstar 2600 and the Betis valve multiport in Latin America or also other facilities close to Chile?
Yes, the multi-phase meter has been delivered in combination with the Betis multiport valve, also from Emerson. To my knowledge, not to South America, but we have the references available from the Middle East and also from Asia with that kind of a solution.
Good. Just trying to look through the questions here. There's one question here about do you need PVT data? It's a good question. Every inline multiphase meter would require some information about PVT. When we talk about PVT in multiphase flow, we talk about phase densities, oil, water, and gas, at the prevailing pressure and temperature, which is the meter is operating at. So that is an input to any meter and also ours. In addition to that, you would need the dielectric properties or the permittivity value of the oil as an input parameter for the reference for the meter. If you are in a situation where you have high water cut flowing wells and you don't have the salinity measurement system installed in combination with the meter, you would need some information about the water connectivity or salinity also as an input parameter. Maybe this is one question for you, Martijn. There's a question about the radioactive source, about safety on an open well site.
Yeah, that's a good question. Well, first of all, not all configurations, as explained by Laura, has the need for the radioactive source. So we have options available for meters without radioactive source, like the 2600M and the MD. In case the flow conditions and the requirements for accuracy are such that the radioactive source is required, we can state that it's delivered with a padlock, so it's bolted onto the meter body, and in addition, the access to the bolt is blocked by a lock. So that prevents that it can be debolted from the meter. And also the radioactive source and the amount of radioactive material that is inside the source container is extremely small, and it's almost impossible to measure the background radiation at a very small distance from the source. So as such, it's safe for the environment.
Thank you. We're having a lot of questions there, so I'm trying to go filter this as we go along. There was one question here about sands and solids in the well stream. That's a very good question. It's a common one. You know, in terms of sand particles, the multiphase meter, I'm talking about the Roxar meter now, is as a non-intrusive one, apart from the Venturi when you have the MV and the MVG, and it doesn't have any moving parts or static parts that's limiting the flow area as such. Now the sensor electrodes are flush with inside of the sensor wall, and they are not subject to any erosion. And in fact, we haven't had any experience where we have seen installation where erosion has affected the performance of the Venturi or the meter. Now from a measurement perspective, sand particles has dielectric properties very similar to oil. So if you have sand in there and traces of sand, that will be measured as part of the oil. But since the dielectric measurements are volume-based, and the volume of sand typically is very small in relation to the total volume flow, sand virtually doesn't have any effect on the performance of the output on the meter. I would like to add to that that Roxar offers a non-intrusive acoustic clamp-on sand monitor that can be integrated with the multiphase flow computer in order to detect, measure, and quantify any produced sand in the well. Maybe Martijn, one for you here. How does the meter account for phase slip?
Yeah, that's a good question. The phase slip is the difference between the gas velocity and the liquid velocity. And in multiphase flow, this is a very well-known phenomena that the gas, because it's lighter than the liquid, is traveling faster through the pipe than the liquid. So every multiphase meter that wants to measure the gas flow rate and the liquid flow rate needs to account for phase slip. The method that is used by the Roxar multiphase meter is that it uses two different methods for measuring the velocity of the flow. So the first method is the Venturi measurement, the differential pressure measurement, and that velocity that is taken from there is representing the liquid velocity. In addition, we have the cross-correlation technology, which is technology that cross-correlates the signals that are generated from the capacitance electrodes. And these high-frequency signals are sensitive for the gas velocity in the flow. So the Roxar meter has a direct measurement for the gas and the liquid velocity. For the configurations where the Venturi is not present, there are facelift models implemented in the multiphase meter that estimate the amount of facelift that is expected at that pressure, temperature, and gas volume fraction.
Thank you, Martijn. Again, moving on, we have a few minutes left. I'm trying to filter these questions here. There's the one question here about if you have a small well that produces less than 15 barrels a day, is that too low to function? It's a good question. The number of barrels per day is also depending on the amount of gas at the same time, because the total velocity through the meter will be the total fluids in the flow, and it also depends on the operating pressure. So if you have, so I really need to, before I answer that, I need more of the information about the actual application, also water barrels, if that's applicable. What I would like to say is that we have a portfolio spanning from less than 1.5 inch size all the way up to 8 inch. So there should be possibilities to accommodate for multiple wells and different sizes of the wells. But specifically for those flow rates, we will need to do a sizing for that. Martijn, maybe one here for you. In terms of communication with the RTU and SCADA system, the type of communication between the meter and the operator system?
Yeah, so the multiphase meter comes with a flow computer, and the flow computer communicates to the RTU or the DCS over Modbus. It can be serial Modbus RS485, or there's also a possibility for Modbus TCP over an Ethernet port.
Thank you. I have another one here. Do you have any reports for the meter performance against a three-phase separator or a master meter? The answer is yes. We have several reports, third-party flow test reports from various test facilities around the world, including in Europe and in the US, both operating in without the gamma source, with the gamma source, in high GVF, wet gas applications, and classic multiphase flow. And they are available upon request, so we can provide you with that. There are some various questions here, Martijn, maybe for you on this one. Various types of hazardous area certificates available for the meter?
Yeah, so for the meter we have, especially for North America, the CSA certification. In addition, we have hazardous area certification for ATEX and IECX, and also AEC for the eastern part of Europe. So the certifications for the electrical certification for hazardous area for North America are available.
Good, thank you. Yeah, one more in terms of generally about yearly service needs and what are the requirements for looking after the meter? Martijn, maybe that's for you.
Yes, typical maintenance interval is once a year, when a health check is required for the multiphase meter. So the meter at that moment must be drained, and an empty pipe check is performed, and that will check the baseline calibration and also do an empty pipe calibration for the gamma system.
Thank you. We have a lot of questions here, so I'm trying to move gradually along. Yeah, there's a question here about improvement in measurement accuracy if we add a gamma system. That's a good question. On our website, on emerson.com/rockstar, you will find the product data sheets for the M and the MEG and all the various modules and options. and you will see the measurement of certainty stated for each of these meters. But typically, there is an improvement in the measurement accuracy, both on water cut, gas rates, and liquid rates, depending on the application and the area the meter is operating. So I would recommend that you just go onto the website and you will find the details available on the datasheet there.
Great. I'm going to call time now, guys. I know we've got tons of questions in the queue, but we are at the top of the hour, so I just want to be respectful of everyone's time. Since we did not get to all the questions, please don't worry. We will be answering all these questions via email in the next day or so, so we will get you a response very quickly. So thank you very much, everyone, for your attendance on the webinar and this wonderful engagement. We really have had a lot of great questions come through. Thank you very much to Laura, Martijn, and Lars for all of their great assistance on this webinar. As I mentioned, we are recording the webinar, and we will be sending out an email with a link to the recording as well as all the resources that were mentioned on the webinar today, including those PDSs, the Advanced Phase webinar, and some other associated resources. So on behalf of all of our guests on the call today, Laura, Lars, and Martijn, as well as everyone at Emerson Flow Solutions, we thank you again for joining us on the webinar, for your incredible participation, and we hope that you have a terrific day. Thank you.